Welcome everyone to my talk on durable integer arithmetic. We already heard a little bit about integers yesterday at Lisa Lippincott's talk. If you attended this, then maybe you will have some deja vus during this talk. If you didn't attend it, I highly recommend watching it because I think it makes a nice dual to this talk. So this is me. My name is Andreas Weis. You can find me in various places on the web. In real life, I'm one of the co-organizers of the Munich C++ user group. We are one of the biggest user groups in the world for C++. We're currently still meeting only online because of the pandemic, but the advantage of that is even if you're not located in Munich, you can drop into our video streams. And also if you're interested in maybe giving a talk at our user group, please feel free to reach out. We're always happy to welcome new speakers. In my day job, I work as a runtime engineer for Woven Planet, and that's the software company that was spun out of Toyota. So we do all kinds of automotive software, and I work mostly on the runtime there, so like the lower level stuff in the stack. So what do I want to talk about today? As the title of the talk says, this is all about integer arithmetic, and my approach is sort of to start by looking at how integer arithmetic is actually done in the hardware, and what are the properties of the operations, how they're implemented there. So we will do a brief recap of this. I would assume that most of you have already heard this at one point in your education or in your life as programmers. But since we tend not to think about this too often, I think like a recap will be in order just so that everybody will be on the same page. Then I will present some use cases for advanced uses of integer arithmetic. And with advanced uses, I here mean like use cases that are not straightforward to solve with the built-in integer types as we have them in the C++ language today. Then we will take a quick look at how the implementation in integer arithmetic in programming languages actually looks like and how that compares to what the hardware does. And then finally, we will discuss how we can expand the capabilities of the integer arithmetic that we have in the language to be able to better serve the use cases that we saw before. And we will look at different approaches here and try to get a feel for what the trade-offs are here and which approach is suitable to solve the problems. So disclaimer, I'm neither a professional mathematician nor a numerics expert, right? So if you, I've obviously put some thoughts into the stuff that I present here, but way less than other people have, right? So feel free to ask questions, challenge everything that I say, and I'm happy to have discussions and take questions at any time during the talk. So really, be encouraged to challenge everything. Also, the notation that I use in the math segments is, as is often the case in math, heavily overloaded and kind of hand wavy. I hope that from the context it's always clear about what kind of operation I'm talking about. If that is not the case, then please raise your hand and interrupt me. So let's get started by looking at hardware, right? So for the following slides, just forget everything that you know about integers in C++, and we're just going to look at hardware. So as you probably all know, we represent integers in a binary representation in hardware, which means we have a positional numeral system, just like we have for the normal decimal numbers that we all know from school. The only difference is that the base is now not base 10, but it's base 2. So we can expand this notation by multiplying each digit with the respective power of 2 that corresponds to the position that it's in. And the nice thing about these positional systems is that all of the algorithms that you learn in school for how to do arithmetic on these numbers usually generalize to other bases. right? So as soon as you have a positional system in some base, and you know the algorithm for that, then you can easily generalize that to other bases. And we will see later some use cases where this comes in handy for computing. So the simplest operation that you usually want to do is addition. And addition is really straightforward. It's like basically the same algorithm that you learned in school, only that we now only have two possible values for the digits, 0 and 1. So whenever we add a 1 and a 1, right, then we have the overflow case that the digit in this place becomes 0, and then we have a carry that carries over the 1 to the next digit. So we see here two examples. I guess like this is not too surprising. You probably have all seen this before. The interesting case here is really, so in the examples, I'm always going to use like 4-bit integers here, simply because that fits on the slide. And in the second example, we see now something that happens quite commonly. If my result is too big to fit into 4 bits, I have like this one carry that goes into the 5th place, and I have to do something with that, right? Because that is part of the result, and I have to make some decision how to deal with that, because I obviously cannot fit it into my 4-bit type. So implementing this in hardware is actually pretty straightforward. It's one of the common circuits that you encounter when you have an introductory course on circuit design. It's called a full adder. And what it does is it basically takes 2 bits, A and B, plus a carry in, and it adds that together to a carry out and a sum. So the basic idea is that whenever, like over the A, B, and C, if all of them are 0, then also all of the outputs are 0. If you have a single bit set in there, then the sum gets set. If you have 2 bits set in there, then the carry out gets set, but the sum is left empty. And only if all 3 of the inputs are 1, then both the carry out and the sum are 1, right? And you can see like the logic for this is quite straightforward to implement with logic gates. It's basically an XOR and an AND coupled together in interesting ways. And this is now again one of the examples where this property of the positional systems that the algorithms generalize comes in very handy, because the full adder is only able to add a single bit, right? But by just putting a bunch of these full adders in series and always feeding the carry out of the one into the carry in of the next, we are able to generalize this to an arbitrary number of bits, right? So this would be a circuit for adding our 4-bit numbers from the example. And this is also pretty much how it's done in hardware. Like the only trick that the hardware does is because the carry has to go through all of the adder stages, it takes a while for the signal to propagate. So in modern circuit designs, you will employ some tricks to make this propagation of the carry faster. But like conceptually, it's equivalent to what is happening here, right? So it's a really simple operation. So let's look at some of the properties that now fall out of this design. So the first thing to notice is that the sum of 2 numbers with n digits in base B is always representable as a number of that same width. So again, a number with n digits plus a carry bit. And you only need 1 bit no matter what your base is, right? So like for the binary case, that is obvious, but it it also generalizes to the higher bases. Like if you look at the little formula down here, you can see why that happens. So like the biggest number that you can get is of the order b to the power of n. So if you 2 times have this worst case and you add them together, then your result is of the order of 2 times b to the power of n. And now the bit basically helps you distinguish whether you're in the upper half or the lower half of this 2 times b to the power of n, right? So if you have the n bits already, and then just the 1 bit to distinguish whether you're in the upper half or the lower half, that's enough. Another thing to notice is that the hardware implementation of this operation has no preconditions, right? So whichever integer I'm feeding in there, it's always like the circuit is always going to work, right? I mean, I have this sort of edge case where like the final carry out becomes 1, and I now have to decide what to do with this value. But there's really no reason why for any input this simple circuit should stop working. So talking about the carry bit now, if I just discard it, if I just do nothing with it, like the carry out just goes to ground and nobody ever reads it, then I will get a wraparound behavior. So what I implement there is basically the modular arithmetic, which is well formalized in mathematics, so we can all reason about it. All nice and good. So most hardware implementations, of course, don't throw away the carry bit, so they signal it somehow, and usually it's signaled via a flag. So this is not considered like an error or like an exceptional situation by the hardware, but it's just like a flag will get set. You can read the flag, and then you can decide what you're going to do with it. Or you can also decide not to read the flag at all, and nobody will blame you. If you accord for the carry bit by adding 1 additional digit to the result, then you are also guaranteed to get the correct result. That means like no loss of information, right? So you need 1 more digit than you had on the inputs. Actually, like 1 bit would be enough, but like since like if your base is bigger than 2, then you will need a full digit. Okay, so this covers addition. So that basically has a set for like unsigned integers and like the addition as the elemental operation. But of course, the next thing that you want to do is you also want to have the inverse operation. You want to subtract. And what you do there is like basically all modern hardware implementations use the 2's complement for this. And the reason for this is that the 2's complement allows you to use the same logic that you were using for the unsigned computation to carry out the signed computation. So you're using the same adder circuit that you had before to now implement subtraction. And the way that this works is it's the same operation. The only thing that changes is our interpretation of the binary values. And the way that this is typically explained is if you want to convert a number to, if you want to flip the sign of a number, so change it from positive or negative or the other way around, the operation that you do is you first flip all of the bits, so it's a bitwise negation, and then you add 1 to the result of this, right? This is how you usually find it in textbooks. And this seems a little bit magical, which is why I don't like this explanation very much. The way that I like to think about it, which is a little bit more mathematical, is what you're actually doing when you're inverting is that you're subtracting your number from the number that has all 1s for every single digit, right? So this is the exact same operation. Now I'm just thinking about it differently, right? Like flipping bits, that is what the hardware does. But mathematically, what that means is I'm going to subtract it from this number that has all 1s. So that is the like mathematically that would be like b to the power of n minus 1, right? That's all 1s. And then yeah, you still have to add the 1 in the end. And one of the reasons why this is a nicer way to think about it is that now again this generalizes, if I now use a different base, like for example, I can also use base 10, then the same trick still works. Like I can do the equivalent of the 2's complement in base 10 by just taking the numbers that has all 9's for every digits and then subtracting my number for it. And then the number that I get is sort of like the negative number in this interpretation. And yeah, this always works because the b to the power of n minus 1, that is the biggest number that I can have, right? So this subtraction always works. I never run into the issue that I already need a negative number there to represent the result. So if I now look at all the possible 4-bit binary numbers that I can have, then I have here always the binary representation and then the unsigned decimal representation next to it. And now I can add the 2's complement representation next to that. And then you will see, like on the left half, for all of the numbers that have a 0 in the most significant bit, the interpretation on the 2's complement does not change. But the numbers on the right in red, now our interpretation of those numbers is that they represent the negative numbers, right? And you see like this interesting logic, like that, like first the numbers go up and then the numbers go down, right? So the wraparound is like if I go above 7, like above the biggest positive number, then I end up at the smallest negative number again. So why does this now work if I do arithmetic? So if we look at a simple example now, I want to calculate a minus a. Then what actually happens here is I have represented minus a as 2 to the power of n minus 1 minus a, right? That was this trick that we did to invert the bits. And then I add plus 1 in the end again to get the 2's complement. And if I now reorder this a little bit, then you see that the a minus a actually cancels out, and the minus 1 and the plus 1 cancels out. And the only thing that remains is 2 to the power of n. And under modular arithmetic, this is equivalent to 0, which is exactly what you would expect as a result if you calculate a minus a. So this is sort of a mathematical intuition why this trick with the 2's complement works here to model subtraction. So if we now look at a concrete example, so here I'm just calculating 5 minus 5, then you can see that like all of the digits neatly cancel out to 0. I have in my carry out, I have a 1. And if I now discard this, as I would do under modular arithmetic, then my result is 0, right? So that's the equivalent to like the unsigned 16 that would be the result if I interpret the whole calculation as an unsigned calculation. And like in the more general case, if I'm calculating a minus b, it's a very similar trick, right? So the minus b again can be represented as 2 to the power of n minus 1 minus b plus 1. Can again reorder the stuff so that the minus 1 and the plus 1 cancel out. And then the result is equivalent to a minus b under modular arithmetic, right? That's sort of the intuition. And if you look at this, then it also becomes clear why you have to do this plus 1 in the 2's complement, right? Because if you just invert the bits, then you basically have this off by 1 error, right? You have the 2 to the power of n there, but you're 1 off, right? You're 2 to the power of n minus 1. So you add 1 again, so that the 1 that you were off after the inversion now gets canceled out, and then the whole thing under modular arithmetic then comes out to the right number. So that's the neat trick here. So yeah, again, if we look at an example, we're calculating 5 minus 3, then we again see like we get the, one overflow bit. But if we only look at the black bits, then we actually get the correct result. And the same thing also works if I have 2 negative numbers. It's basically the same trick. Only that now I have 2 times the 2 to the power of n remaining. But since modulo basically means like keep subtracting 2 to the power of n until you cannot subtract it any longer, it's the same thing, right? The equivalence still comes out at the expected result. And yeah, this would be one example for adding two negative numbers, so to speak. And you can see how it comes out. Any questions up to this point, please?
So what happens if you get an underflow, if you subtract -5, -5, so if it runs out of the range,
if you calculate -5, yeah, exactly. So that is, so yeah, it depends a little bit on how you on your interpretation of the words overflow or underflow. I would still call that an overflow. It's just a negative overflow, and you have to detect that, right? Because like what would happen if you just look at, like if you calculate -5. So what are we now actually doing? So it's -5 plus -5, right? So what we are calculating, like -5 in the unsigned case is just 11. So under the unsigned interpretation, it's just 11 plus 11. So the result would be 22. And we don't have, like in our table up here, we don't have a reasonable interpretation for that value 22, right? So we need to decide, how we're now going to interpret this result. And that is actually exactly what we're going to take a look at next. Because in the unsigned case, it was very simple, right? We always had to look at like what falls out of this carry out, like what is the red digit that comes out of here. And if that is 1, then I know I have to expand the result. But in this example here, like 5 minus 5, this result is in the range, right? Like the 0, that is a number that I can represent. So this is not an overflow condition, right? There's nothing to report here. It's all good. Similarly for this, like 5 minus 3, again, the result is 2, right? That's a valid result. Nothing to report. But I do have a red 1 in front, right? And I can keep going, like also the third example, still the same. But then on the other hand, if I calculate 5 plus 6, the unsigned result would be 11. But if you remember our table from before, like all of the numbers with a 1 in the fourth place are the negative numbers, right? So under my sign interpretation of the results, the 11 would be interpreted as a negative number. So this is actually now an overflow condition, even though I have a 0 in my final carryout. And this is now, I think, actually the case that you were talking about, right? Like when I overflow in the opposite direction, right? So looking at the carryout, as we did for the unsigned, is actually useless for reasoning about the overflow condition for the signed operation, which is why in hardware you usually have two different flags for indicating overflow. So the unsigned is usually called carry, and the signed one is called overflow. And the signed one is a little bit more complicated than the carry, because you need to look at the inputs to figure out whether you actually ran into an overflow condition. But it's still, yeah, it's just a couple of logic gates. So what are the properties of the subtraction now? So the nice thing is it's carried out using the same logic as the unsigned addition. We're just interpreting the result values differently. That also means, like unsigned addition, there are no preconditions, right? This circuit always works, it always gives a result, and we just have to decide how we interpret this result. The overflow condition changes. It's now no longer enough to just look at the carry flag. Actually, the carry flag doesn't really have any meaningful semantics, as far as I can tell, for when I'm doing signed addition. And yeah, the wraparound is that if I flow over the biggest value, then I start out at the slowest value again, right? So that's actually all I have to say about subtraction. So the next thing to look at is multiplication. And here, again, the algorithm is pretty much the same as, you know, like the long multiplication algorithm from school. I noticed that like different countries have different notations for teaching this in school, so I hope this is understandable. Basically, what I do is, like for the one operand, I always like in this case here, the operand on the right side, I just keep shifting it with every row. I shift it one position to the left. And then the second operand determines whether I actually include this row in the addition or whether I discard it, right? So if the digit on the left is 0, then it's 0 times whatever's on the right. So I just discard it. And otherwise, I just end up with the sum. I sum it together, and that's the result of my multiplication. So in hardware, this is again quite straightforward to implement. Like we already know how to add numbers. Now I just need to be able to shift numbers, and like shifting is even simpler than adding. So this is really straightforward to do. And fortunately, it also works naturally for negative numbers in 2's complement. I have to be a bit careful here with the sign extension, because like for unsigned numbers, basically all of the digits expanding to the left side will be zeros, whereas for negative numbers under this 2's complement implementation, it will all be ones. So I have to be a little bit careful about like what I do there on the left side and at which point I actually start discarding ones. I'm not going to show examples of this because I think it's rather boring. So the biggest result of the multiplication, if I again look at the worst case, multiplying two numbers by the power on the order b to the power n, the result is of the order b to the power 2 times n. So that means I will need, in the worst case, twice the number of bits that I had for the inputs, right? So this here is like for our 4-bit integer case, this is exactly this example. So it's now no longer enough to just have a single flag. I actually need like basically 2 results. So like double the width of the inputs. Exactly. So the overflow condition is now when the upper half of this result is not 0, right? So if it's all zeros in the upper half, I can just discard the upper half completely and just fit it again neatly into like my 4-bit int, for example. But if there's a 1 anywhere there, then that constitutes an overflow. Like the addition, again, the hardware implementation here has no preconditions, right? This always works. With the overflow, again, I typically report it via a flag. And in most hardware implementations, I have a shortcut that actually doesn't calculate the entire upper half if I'm not interested in it. So as soon as it realizes that one of those bits in the upper half will be 1, it will just set the overflow and be done. But hardware architectures typically provide both forms, right? So if I want, then on the hardware getting the full result without loss of information, that is usually possible. Okay, and that's actually all I wanted to say about multiplication. Then the last one, the last operation is the division, and this one is significantly more complicated than the others. So I'm not even going to bother to try to explain how hardware does this. If you look at, like if you do circuit design these days, then you typically don't place the logic gates yourself on the board, but you have like a synthesizer that does this for you. So you basically write an implementation in a higher level description language like Verilog or VHDL, and then you have a synthesizer, which is basically a compiler that transforms this code then into actual logic that goes into the circuit. And like for division, like for addition, subtraction, and multiplication, if you're implementing this in VHDL and Verilog, you just write it, right? You can just write A plus B or A minus B, and it will know how to synthesize the circuit. And there's usually really no reason to do anything more complicated because it's super straightforward what it has to do. For division, this is not the case. So like the standard for Verilog, for example, has a division operator, but many synthesizers don't implement it. And even if they do implement it, it's often not implemented in the way that you want it. So this is, like, compared to the other operations, this is really non-trivial and like a whole different deal. Also, those division circuits are quite inefficient compared to addition and multiplication. They introduce large signal delays, are usually slow to execute. So yeah, not nice. The underlying algorithm here is the long division algorithm, again, that you all know from school. And then like one property that arises from this is that whenever I do a long division, I get the remainder for free, right? So I get the quotient, the integer quotient as the primary result. But by computing this, basically the remainder falls out of the computation naturally, right? And the same is true in hardware. So in this sense, as with the multiplication, if I want to get the full result without loss of information, it's actually a double width result, right? Because the remainder is also part of the computation that I just did. So in particular, in cases where I am interested in the outcome of the division as well as the remainder, I only need to do the calculation once, right? So it makes sense in many cases to have this as part of the result of the operation also. Signed division can overflow, but only in corner cases. Those of you who were at Lisa's talk yesterday might remember this. The ugly case here is if you have the smallest negative number and you divide that by -1, then you don't have a positive number in your representation available that could map to. And this is an overflow. But since it's such a corner case, it's very often treated differently from the overflow in the addition and the multiplication. So like on x86, for example, where all of the other overflows are reported through flag registers, division actually does not set any flag registers. It's an exception in this case. So that's a bit weird. The other thing that is weird is that the division is the only of the elemental operation that has a precondition. And it's also a really specific precondition because that you cannot divide by 0, right? And this is, of course, due to 0 being an absorbing element of the multiplication. Whenever you multiply anything by 0, the result is always 0. That's why you cannot invert this. And unfortunately, you really cannot invert this, right? Even if you try to come up with like some extension to the algebra of natural numbers in which this operation makes sense, to my knowledge, such an extension does not exist, right? Like all the stuff that you come up with is not very meaningful in the end. So this is really a precondition. And what hardware typically does is it traps, right? So it's again like a hardware exception or something. So this is really a hard error that you can't just gloss over like the overflow for the addition, for example. So this is all I want to say about the hardware. So to summarize, the important points are that the behavior of all the elemental operations is well defined for all the inputs, with the exception of this one case that I cannot divide by 0. But like for all of the other cases, I basically can just keep going. The overflow conditions are typically signaled through flags. There are some processes that signal it by other means, but they are really the exception. All operations can be carried out without loss of information for arbitrary inputs. If, like for plus and minus, you look at the overflow flags, and for the division and multiplication, your result has double the width of your inputs. And yeah, computing the quotient gives the remainder for free. Please.
Is GPU hardware basically the same in these cases?
The question was if GPU hardware is the same. So the thing about GPU hardware is that it's mostly concerned with floating point computations. So they don't do, like you can do integer arithmetic there, but it's typically not very fast. But as far as I know, And I'm not 100% sure, but as far as I know, it's the same. Yeah. Yeah, and I'm not actually sure what would happen on a divide by 0 on a GPU, because it's like raising hardware exceptions on GPUs is not that easy because you have all of these threads running at the same time. So yeah, but that's an interesting question. I would have to look that up. I'm not sure. Any other questions about hardware before we dive back into the software world again? Okay, good. Then let's actually look at some use cases where I would be interested in this. So the first thing that comes to mind, and like what is probably the example that most people worry about, is safe integers, right? So if I have such an integer overflow condition in my computations, it's almost always a bug, right? And even if it's not a bug, like I probably cannot accept loss of information in these cases, right? I cannot just silently wrap around. That usually does not make sense in the context of the program logic. So the idea behind safe integers is simply to say, like, if an overflow condition occurs, detect it and like prohibit the program from just going on. The problem that you're probably all aware of is in C++, such overflow checks are kind of difficult to implement, because the problem that we have in C++ is the overflow is undefined behavior. So I cannot just carry out the operation and then check, for example, if the result is wrapped around, because if the operation is ever carried out, I already have undefined behavior. And the compiler is allowed to optimize based on the assumption that undefined behavior never occurs. So if I'm unlucky, then the operation might actually never be executed on the hardware. And if you have seen Fidor's talk earlier this week, then he goes into great detail about this. It's talk on undefined behavior. Timo, please.
I have a question. So
yeah.
It's interesting that there is this like difference between like in hardware, overflow is always well defined.
Yeah.
In C++ and CP.
Right.
I wonder whether it's because and like until C++ 20 it wasn't even defined that like integers are like percent integers are Two's complement.
Yeah.
But like specifically about the undefined behaviors.
Yeah.
I wonder if it's because C++ is designed to run on machines that are different from everything you just presented, or
yeah.
whether it's because the optimizations you can get, if you do declare that to be UB, are so significant that that performance benefit is the motivation for it.
Yeah.
So
yeah.
I wonder which one of these two is the motivation
right.
for saying this is UB.
Yeah. So Timo makes the very correct remark that there's a disparity here that is kind of obvious, and the question is now, like, where does this come from? And I think like both of the things that you suggested are true. Like in the beginning, like if you look at K and RC, then it actually says like the result after the overflow is machine dependent. So it's not undefined behavior. It's just that we're not going to tell you what the result is going to be.
Okay, you can
and
that value and print it, and that's fine.
Exactly. Yeah. Like you could still access the result. You could still continue running your program. It's just that, like, yeah, the result might not have any meaningful value, but your program is not broken. And at some point during the evolution of C and C++, that changed into its undefined behavior, and compilers are now allowed to optimize based on this. And right now we are in the unfortunate position that these optimizations are so dear to us that we're not willing to give up this undefined behavior and sacrifice the optimizations that it allows. That was basically, if you followed the discussions surrounding J.F. Bastian's paper about changing the standards so that integers are specified to be Two's complement, like it was very easy to, like comparatively easy to argue that like on all hardware architectures that we're targeting today, the implementations use Two's complement. And like basically discouraging or like disallowing compliant implementations on like ones complement machines or sign magnitude machines. but we were not able to remove the UB on the addition. Like even if you know that on a two's complement machine you will get the wraparound, we didn't want to give up the optimizations, right? So it's, yeah, the focus here changed, right? It's like we started out in one place and then it became a different thing over time, and like that is actually one of the takeaways from the talk, I think, that we're now in this situation, right, where we have this operation that does not really map well to the hardware that we have underneath, and that actually causes problems. Sorry for that. And that causes problems, and I probably, like, therefore cannot rely on the built-in integer types for some use cases. So this is where we were. Yeah. Okay, so yeah, this is difficult to do in C++, but it's actually a vital use case for many domains, right, as should be obvious. The other thing that I think many of us would like to do from time to time is arbitrary precision arithmetic, in particular like big numbers, right? Like you probably often see this like on some HackerRank problem, or like if you do what's it called, like Project Euler, where you have to solve math problems. Often the result is too big to fit into 64 bits, and then you have a real problem in C++. So because of these properties of the of all of these algorithms that they generalize to arbitrary basis, it's very easy to just do this in software, right? Like basically save my number as just a list of bits and then perform all of the calculations in software and store as many bits as I need to represent the result. Of course, if I do this in a bit-by-bit fashion, this is very inefficient and quite slow. So what I really want to do is like sort of lift the implementation to the base that is the word size of the machine, right? So I carry out an integer addition on a 64-bit integer, right? And I break down my big number into 64-bit chunks, and then I just chain them together like we did for the 1-bit addition, right? I always propagate through the carry, and then do that as much time as often as I need for the bits, right? And yeah, so like for these cases, it would be really nice to be able to get like the full width result of the multiplication, for example, or to have access to the overflow and carry bits. The third use case, this is a bit of a tangent, but I still wanted to include it here because this was actually what got me down this rabbit hole. So I was working on a number on a library for rational number arithmetic. And I was really bummed out that, like for rational numbers, you run into this case that you cannot divide by 0, right? So you all of a sudden now have all of these invalid values for your rational numbers lying around, where like if your denominator is 0, then like your rational number does not represent any value. But then if you look at IEEE floats, they actually do assign meaning to these cases where you divide by 0, right? They introduce these special values, like the positive and negative infinities, and this not a number value. So I was wondering, like, couldn't I do the same for rational numbers, right? And thereby have a data type that supports all of the elementary operations without preconditions. And I did a bit of research, and it seems that the rational number type in Android actually supports this. Like they support these special values, and like whenever you convert to float, they just naturally map to the IEEE values. But they don't implement calculations on rational numbers. And here the interesting thing is, so like the like how IEEE motivates these numbers is that they basically say like they're anyway the limiting case of the operation, right? So like you ran out of the precision that you have, but like in the limiting case, this is still the correct result. So like mathematically, it makes sense to like jump to these values. But this requires you to be able to argue about limits and convergence. And for that, you need real numbers and not rational numbers. So you run into some interesting corner cases here with the rational numbers. So like, for example, when you do actual calculations, like one of the things that you can do very easily with floats is that you want to approximate irrational computations. And a usual technique for doing this is by, like, for example, I want to calculate the exponential function, which is Euler's number to the power of x. And the way that I can do this is I just do a Taylor series expansion. So for those of you who are not familiar with this, it's a technique that allows you to basically transform a differentiable function into a polynomial, right? Like if the polynomial had infinite degree, then this converges to the correct result. If you only have finite precision, you just decide I'm going to cut it off here, and then you get like as much precision as you basically want. And it's quite easy to understand. You just need a little bit of calculus, but it's rather straightforward. So what if I now try to calculate, like with my rational number library, Euler's number through such a Taylor series? And then the interesting thing that happens as I get more and more precise, the numbers for my numerator and denominator get bigger. And this is particularly problematic if I now do a follow-up calculations. Now let's say I want to calculate like the cubic power of Euler's number. And I do this by just, okay, I implemented the Taylor series expansion for calculating Euler's number. And now I'm just going to cube it, right? I'm just like the result of the first one, x times x times x, right? And now what happens is my numbers get huge. And they get huge in unpredictable ways, and they overflow pretty quickly. But you see here, it only overflows like on the step number 6, but it doesn't overflow on the step number 7. And if instead of doing it this way, I do the Taylor expansion for the third power directly, so like not first computing Euler's number and then cubing it, but doing the Taylor series for x equals 3, then I also don't get the overflow. Then I get a completely different behavior. Like the series takes a lot longer to converge on the correct result, but like the overflow behavior changes completely, right? And that is quite interesting. And I got a little bit nerd sniped by this, and I was wondering, like, how could you meaningfully solve this? And when I wanted to run experiments, I frequently ran into this roadblock that, like, whenever I run into an overflow and I want to meaningfully handle this, it's just super difficult. And it's unreasonably difficult because, like, if I do the calculations in assembly, it's really hard. It's really straightforward to handle the corner cases, right? Because I always get a flag and then I can decide what to do. But in C++, it was just super hard. So yeah, I thought like this, yeah, like I wanted to have fun with math, and C++ made that more difficult than it should have been, right? So yeah. If anybody knows whether this is an extension that makes sense, I would be happy to talk to you after. But I thought it was interesting. So now to the title of the talk. What do we mean? What do I mean when I say durable integer arithmetic? I want to solve these use cases in C++, right? And I want it to be easy, right? I don't want to have the situation where writing an algorithm in assembly is actually easier than it would be in C++ because of how the built-in types work. So the hardware instructions were designed to be flexible, right? The hardware needs to be able to solve all the problems that people could run into, but we lose some of this flexibility in the abstractions. And I would also argue that this is actually the fundamental thing that you want to do, right? So if you want to have safe integers, if you want to have arbitrary precision arithmetic, this should be the first thing that you ask for, because this is the building block, right? Once you have this in place, then solving those other problems becomes so easy that like you can do it on your own. You probably won't do as good a job as a numerics expert would do, but it's now within reach. Whereas if you don't have this, then this is just so hard to do that you basically have no chance. So that is basically my take on this, right? Like I really would like to have some capability in the language to like do these sort of low-level, close to the hardware in their semantics types of operations, as we've seen this. Yes.
Can you solve most of the corner cases except for maybe divide by zero, obviously, by simply limiting the size of integer values that you utilize? So if you've got a 64-bit machine, the largest representable number maybe is a 32-bit, and so therefore,
right.
Calculations
Yeah.
stay
Yeah.
within bounds.
Yeah. So the question is, can I solve these problems by basically widening my input types so that the result will always be representable in this widened type? And yes, you can do. The problem that you then run into is then that like you're adding two int32s, and the result of that operation is now an int64. Now, what if you want to add to that number again, right? So at one point you have to shrink again, and that's what makes this not nice. I guess, and I haven't actually tried doing this, that you could try wrapping this in sort of a monadic interface where you say like, okay, like this 64-bit number is actually a value that is representable in 32 bits, and then have like a monadic interface for composing your arithmetic operations. But I have no idea what that would look like, and if it would still be something that I would want to use for calculations. So, but yeah, in principle, I think it would work. As long, of course, as the hardware supports the larger data type, right? So if 64 bits is already your base type, then you run into trouble. Yeah. So how can we get this? And like, can we get this anywhere today? So what do programming languages implement? So I looked around at like, what's out there? So one thing that I actually found, which I didn't know before, is there is an ISO standard, 10967, about language-independent arithmetic. And it specifies how you should do integer and floating point arithmetic. It was worked out by the now disbanded SC22 WG11, which is like sort of a sister committee of our beloved WG21. This was titled Binding Techniques, and what they were trying to standardize was like basically programming language independent concerns, like, for example, arithmetic or like how types look like and stuff like this. And they published a couple of standards. This one was by far the biggest. So what they do is they mandate that the error states such as overflow, exceptional values, divide by zero, all of this kind of stuff is modeled explicitly in the language. So, right, so your result type needs to be able to represent these error states. They do not specify double width operations, which I found a bit surprising that they seem to only care about overflow here. But that doesn't really matter because as far as I can tell, nobody ever bothered to implement this, like in the sense of, hey, I'm claiming that I'm compliant to this standard, right? So it's an interesting document because I think like mathematically what they specify there is very sound, but it looks like, yeah, it's a dead standard, right? I'm not aware of anybody actually ever going ahead and implementing something based on this. So back to the real world. What do we have in C and C++? So for built-in integer types, obviously, signed overflow and division by zero are undefined behavior, leading to all the problems that we already touched upon. So as I said previously in the discussion with Timo, historically this was not the case, but at some point it just changed. And now because we have these heavy compiler optimizations, We even do, and this is quite interesting, like if you look at the x86 assembly for addition, it uses an opcode that doesn't even set the flag, right? So when you generate machine code for addition, you usually use the low defective address opcode, because that is, I think it's because the opcode is a little bit smaller, and then your binary output is smaller and thereby more cache efficient. So it's not a big optimization, but one of the results of this, you don't even get the flag anymore. Timo.
So wait, did I understand this right? Like CPUs have instructions for doing the addition, for example, or the multiplication properly, but no higher level language is ever going to, no compiler is ever going to emit instructions that hold these?
C and C++ compilers are not going to emit those instructions. Other compilers, other languages, it's a different story.
Interesting. Very interesting.
And we will see that in a little bit, yes.
So in C++, you basically never get these instructions emitted.
I think if you compile like with GCC with optimizations enabled, I think it's really hard to get an actual like add opcode on x86 emitted, yes. Yeah.
It depends on your architecture too. Like different CPUs, there might not be options, right, to execute instructions without the flags getting set.
Yeah, that's a good point. So the comment was that this, of course, highly depends on the machine architecture that you're targeting. So like on x86, it's a problem. On other architectures, it might not be. Also, our integer types are subject to arcane conversion rules during computation. Again, I refer you to Lisa's talk from yesterday if you want to dive into this. If you value your sanity, I suggest you don't. Interestingly, compilers are able to optimize double width division pretty well. If you do a division followed by modulo on the same input arguments, you usually get like only a single division opcode emitted, and it does the double width thing. For double width multiplication, I have not found a way to trick this into using the wide multiplication opcode. The bottom line here is like this behavior has grown historically. In the 1970s, I think these were good results, right? We had very, very different hardware architectures there. We had a very wide variety of hardware architectures that we were trying to target. But they have not aged that well. They're very limiting today. I think they do work reasonably well for like the everyday use case. Of course, there's also problems. But like for these more advanced use cases, for the like what I call like the durability cases, doesn't really work that well. And unfortunately, because we value backwards compatibility, which I think is a good thing, this is unlikely to ever change for the built-in types, right? So if we want to change this behavior, we need either new types or a different means of performing the computations. So now coming to other languages, what do like the blessing of the late birth, does that help? So Go is probably of the modern languages the one that is closest to C in spirit. Go silently wraps unsigned overflow, right? So it's not undefined behavior. It's actually like it's guaranteed to wrap around as expected under 2's complement. They don't have, as far as I could tell, I don't know Go that well, but I couldn't find any like standard library support or built-in support for doing like checked operations or double width operations, which is a bit unfortunate because I think like in many cases you still want to be able to detect that you had an overflow, but at least since it's not undefined behavior, it's a little bit easier to detect. Perhaps to no big surprise, Rust seems to be doing everything right. They have this interesting behavior that in debug mode, they panic on signed overflow, and in release they wrap, right? So they still somehow consider it an error, but they also acknowledge that like in release mode, you might not want to be willing to pay for the check. And this is unique. I don't think any other languages does this actually as per the specification. They also provide library functions for checked arithmetic. Actually, like library functions is probably a bit misleading here because these are like member functions on the standard integer type, right? So as soon as you have like an I32, you can do like dot checked addition, and thereby get like checked arithmetic that like reports back if you have an overflow. Please.
An interesting Rust library feature I know that they have is you can specify that there's an integer that's non-zero,
Mm-hmm.
and so we'll just use the zero as sort of like an invalid state.
Oh, that's interesting. So the comment was that in Rust you can specify like a type where like 0 is not like a valid value of a type, but it has like special meanings, so you can interpret it as like an error state for integers.
You do like an optional non-zero int, and it will optimize for just being the size of an int, and you'll use zero as no integer.
Right. Yeah. So like if you're doing an optional non-zero int, then it's basically able to optimize away the overhead for the optional by factoring that into the 0 state of the integer. Yeah. They also have double with multiply, even with carry input, which is very useful when implementing like these big number arithmetics. But they don't have double with division, and I think the reason that they don't have this is because compilers are so good to optimize this already. That's my assumption. I'm not sure, but makes sense to me. Also, Swift also does this mostly, right? They have overflow as an error by default, but they provide special operators for wrap. So like you have like the plus operator, and then you have like, I think it's the plus ampersand or something like this, which is then the operator that allows overflow. So you can, like if you want it, you can get it without too much syntactic overhead. They also have library functions for checked arithmetic. They have the double with multiply and the double with divide, but they don't have the carry input. So here, when you want to propagate the carry, you have to rely on the compiler optimization. But this is also, as I have an example later, this also seems to be something that compilers are able to do in principle today. So what I would really like to get for C++ is like, so this is the example in Rust, right? I can just do integer 1 checked at integer 2, and I get the machine code on the right. And as you will notice, the only thing that it does is it does the normal addition, and then the set NO that basically says if the overflow flag was not set by the operation, then set the value in the AL register, right? So it just carries out the operation and then just writes out the flag. That's all it does. So yeah, I really would like to get a minimal set of fundamental operations that do this mapping to the hardware nice. And the reason that I want this is because I think they will be useful building blocks, right? I don't want users to like replace their ints by like this low level closer to the hardware thing. I want like library writers that want to write like a safe integer library to be able to use this to make their job easier. Yeah, so it's mainly targeting library developers. And also like instead of having to wait like for a safe integer library to go into the standard, for a big number library to go into the standard, if I have this, like I can democratize the thing somewhat, right? It's now much easier for like a normal developer to provide such a library and just put it on GitHub. So can I get this today? I did a few experiments. So maybe the compiler is already smart enough to do nice machine code if I just do like the manual overflow check. So I went to Stack Overflow, how to check for integer overflow and addition. Then you get like some code like this, horribly convoluted, but that's the price you pay for not invoking the undefined behavior. And lo and behold, the generated machine code is pretty horrible. So what I would have liked to see on the right is like a similar machine code that that Rust gives me, but I don't get that, unfortunately. I have to do like branches and testing and stuff like that. So yeah, And like, I don't blame the compiler for this. Like this code was way too complicated to detect this pattern, right? Like, please don't waste your time implementing this. It also cannot detect double with multiplication. At least I don't know how. And like the double with division, that's really the only one that it can do. Compilers are aware of this problem because they do provide compiler-specific built-ins that allow you to do like basically like a checked addition, for example. So you can do it, but then your code will be machine-specific and non-portable, and you need different source code paths for different. Please.
Machine-specific or compiler-specific?
Compiler-specific, yeah. So yeah, the question was whether it's machine-specific or compiler-specific, and it's compiler-specific. It seems unlikely that this will get much better because, as I said, like, yeah, expecting the compiler to figure out my complicated overflow check from the slide before, that's just unreasonable. So attempt number 2. I'll just write it in assembly, right? I will just write an integer library that is written in assembly, and then I can do whatever I want. So I did that. Like, I'm not an expert in assembly, but like a naive implementation that just like does checked addition, writes out the overflow to a new field, and then I can access that from C++. And I did some benchmarks. So what I did here is I was using the Bresenham line drawing algorithm, which is like a famous integer algorithm. And I was just having like a small array, small enough that it fits into a single cache line, and I was just drawing a bunch of lines there, right? I was drawing lines into all directions, so I get a little bit of branching and like a lot of arithmetic. And what we see, like the first, and yeah, so this, and my benchmark does not overflow in any case, right? So like I check for overflow, but it never actually does overflow. So the first is just like using the built-in integer types, and that's nice and fast. The second one is using my library. So that means I'm like for the integer addition, for the multiplication, I'm calling out to this assembly library, but I'm not checking the, I'm not actually checking the overflow flag, right? I'm just getting the result back and continue computation. And the third line is I'm now also checking for the overflow and have like all of this code that says like in case there was an overflow, please set the integer value to an invalid state so that we can continue safely, and then the invalid state just propagates through the following operations. Exactly, and as you can see, it's a lot slower than the built-in ones. So why could that be? I have some theories. First of all, there's the function call overhead, right? Like to do a function call, I need to go like through all this prolog thing, which these are instructions, I have to do that. There's bad caching behavior, right? My assembly library probably lives in a different part of the code than the instructions for the calling functions. Maybe that has an impact. I would expect this to become hot in the cache pretty quickly, but it could have an impact. What I think really is a big problem is the register pressure on the caller side. So what that means is whenever I do a call into an external function, there is a contract specified in the binary interface of the platform which registers this function that I just called is able to just override with its own value, right? And now as the caller, if I have put some values into one of those registers that I will still need once the called function has returned, I need to save those values on the stack, right? So basically, I don't have as many registers available as I would have, right? Because like for an addition, this function, like it will not need a lot of registers to carry out the addition, but because of the binary interface, I have to assume, since I don't know what the function is going to do, I have to assume that all of the registers which are not preserved by the caller will be overwritten, so I have to save them. And that just constrains the compiler in a way that it's not able to generate code as efficiently as it would be able to if it could see all the code in one place. And like there's zero optimization opportunities for like reasoning about what's going on in this function. And you might think, well, maybe this changes if I use link time optimizations, but it does not, because link time optimizations only work if the function that you are calling was compiled also by a C++ compiler, and that compiler emitted like additional information about this function that can now be used for the optimization in the later stage. If you just write your library in assembly, the assembler is not going to output this information, so it doesn't work. So this gets the job done, but the resulting code is not what I would consider ideal. It's hard to optimize, not nice. I would claim this is not really suitable as a building block. So I don't think that this is a problem that can be solved by a third-party library because of this. Right? Like these are the two options that I would have seen for solving this outside of the standard, just as a normal user, and they both don't seem to work. So what about standard library extensions, right? So because standard library functions are not ordinary functions, the compiler may use like the special knowledge, since their semantics are well defined by the standard, to apply optimizations that it could not apply to built-in functions. And again, like Fedor Paikas in his talk on undefined behavior, I think gave some nice examples for this. Furthermore, a lot of this functionality is already being provided by compilers in the form of these compiler-specific built-ins. So we would be standardizing existing practice to some extent. So it seems to be a good match. And people have actually been doing this. So the furthest along up is probably the C committee. They have discussed two papers which are closely related. The more fundamental one is this one, Towards Integer Safety, by David Swoboda. And this seems to be on track for C23. So we might actually get this really, really soon. So what they provide is basically something like this. You can add two numbers. The result will get written to a third place, and then you get a Boolean return value that tells you whether the thing overflowed, right? So if the function returns false, then an overflow occurred. Otherwise, result will contain the correct sum. These functions are specified in a way of saying, like, we assume that the calculation is being carried out in infinite precision arithmetic, and then if the result is something, then we do something. And as we've heard yesterday from Lisa, that's not a very nice way to specify this. It would probably be cleaner to specify it in terms of types that we actually have inside the language. And also C wants to implement this with macros because it's C, right? So, yeah. They seem to be mostly concerned about safe integers here, like the title already suggests. So it really only addresses overflow, not really like these use cases for multi-precision arithmetic. So it's, yeah, like if you want to write safe integers, then I think this will be super useful. For the other use cases, unfortunately, probably not that helpful. But we've also been talking about this in WG21, the ISO C++ committee. So SG6 has one proposal from Lawrence Kraull, which has been around for a couple of years, that adds a whole bunch of new operations, which covers like everything from like detecting overflow, white multiplication. It adds these functions for splitting and joining results that Lisa also had in her talk yesterday. It even adds special fused operations for multi-word arithmetic, like a double addition or a multiplication coupled with an addition. So these are like really specialized instructions, like not even Rust or Swift have them, but they like if you really want to write like a high performance big number library, then they will probably be really handy. So it covers a very extensive range of operations, and if you want to track the progress on this, I think you now need to look at this other paper, P1889, which is like sort of an overview paper that encompasses many different papers from the SG6 group, and I think that's the number under which they discuss it now. Lisa Lippincott also wrote a paper which provides functions that allow you to check boundary conditions, right? So what you can ask here is like, given the numbers a and b, is it actually safe to perform an addition on them? Like, will that overflow? And it's a very extensive list, again, of functions for all kinds of conditions that you might want to check. So the way, like, if my understanding is correct, then these are not really intended to be used for implementation in a safe integer library, because like in a safe integer library, it makes much more sense to just carry out the information and then check afterwards if the result is valid. But they are really useful for like checking and expressing contracts, for example, right? Like if you want to, like, just I've written a function, and I don't want you to call these functions with values that overflow. How would I express this, right? And this is a very clean and succinct way of expressing this. Again, referring you back to Lisa's talk yesterday for how you would have to do it otherwise if you don't have these functions. So are there any caveats to these library solutions? I've thought about this for some time. Like, for example, when I have a function, I'm still bound to the calling conventions of my target platform. So does it actually make a difference whether I have the first signature, where the result is written back to a pointer that I gave as an argument, versus the second case where the return value is basically like a double with result, right? Where there's like one integer in there and then room for an extra flag. And for the calling conventions, this does make a difference, right? Because in the second case, all of my results are placed in registers. For the first case, I will need an external memory location where the result goes in, right? However, I do think that for this, if it's a standard library solution, worrying about those concerns is probably not going to matter. Because of this fact that the compiler will most likely like know what these mean and treat them in a special way anyway. I really, really hope that they won't be put under the same constraints as ordinary functions for this. So yeah, and furthermore, we anyway absolutely do not want to have the full function call overhead for this. So I think like it's in the best interest of implementers, of compilers, to treat them special once they're there. So I hope I hope that like worrying about the interface here is really not a concern. So yeah, like the way that I envision this is that the compiler would map this to the same functionality that is these days available through the compiler built-ins or intrinsics. Of course, we cannot enforce that in the specification, but yeah, as I said, it's in their own best interest for the compiler implementers. So that leaves the question: is there actually sufficient room for doing this, like for solving this problem in the core language, or is it really that that library solution is good enough and gets us there all the way? And I think like it's really enough to have it in the library. Like I ran some experiments, and I think that like compilers are good enough these days at doing like this special reasoning about standard library functions that it's that we don't need core language support. So in particular, like even complicated things that were not possible a couple of years ago, compilers can now do. So this is an example of doing an add with carry, right? So I'm using here one of the x86 specific compiler intrinsics. that are available on GCC and Clang, and I think even also on MSVC. So what I'm doing is I'm basically doing a double width addition here, right? So I have two sets of 32-bit number that represent a single 64-bit number, right? And now I'm performing the addition in two steps, and the carry flag from the first addition is the carry in for the second addition, right? And like you can see, like in C++, so the carry is a return value. I have to save that into a variable, and then it goes as an input parameter into the second function call. But the compiler is smart enough to recognize this, and you see in the machine code on the right that the add with carry, the ADC, follows immediately the add opcode, right? So it's just like the add opcode sets the flag, then the carry value is in the flag register, and I just call the second addition immediately after that. And I don't need to copy the carry around or something like that. And like this makes me really optimistic, because this was actually one of the cases where I was not sure, like, is the compiler actually able to do this? Or because if the compiler always would have to copy the flag out, copy it to a different location, and then feed it again in as an input to the next opcode, like that's just a lot of back and forth. But it seems to be able to be smart enough to like do transformations like this and just lead to really compact machine code. So yeah, that's pretty much it. Wrapping up, I think like, yeah, the hardware behavior, that's what we should consider the fundamental building blocks for integer arithmetic, for what like advanced algorithms will want to do. And the built-in integer types, unfortunately, just don't do a good job at mapping to them. But since this is a pretty common problem, we already have well-established solutions in the field for like how to model this. It's just that they're not part of the core language of C++, like not part of the core specification, not part of the standard. However, I do think that like SG6 is actually doing good work, so I hope that they will be able to ship this soon. And I think once we have this in the standard, we have a good chance of like being able to compete with what is state of the art in other languages. So here's some references for you, and I'm happy to take any more questions. Please.
So are you familiar with Boost library, safe integers, or safe?
Oh yeah, that's a good point. So the question was about the Boost safe integer library. So I actually benchmarked that as well to look at the code gen. So the thing about the Boost library is that it allows very flexible error handling, right? Which requires quite a bit of logic just to handle all of these cases. So yeah, it generates a lot of boilerplate code already because of this. But it seems also like I could not get it to the point where it would do like for the core operation this simple of just like add and check the overflow flag afterwards. It was also emitting more complicated code there.
I mean, it would probably have to be built into that library, right? That it would use the intrinsics under the hood.
Exactly. Yeah.
Essentially, to make that happen.
Yeah. So yeah, right. I mean, like, and also like we also have a multi-precision library in Boost, right? And the way that they solve it is they just say like for the most efficient implementation, they just rely on the GNU multi-precision library, which writes its kernels in assembly, right?
Actually, I believe it can rely on that one, or it has its own.
Exactly. It also has its own, but the GMP is the most efficient run, right? That's sort of the gold standard. So that's how they solve the problem. I guess you could do a similar thing for the safe integers, but just saying like for the compilers that we know that have these built-ins, we would just map to this. But I don't think it does that at the moment.
I don't think so either.
Yeah. Mm-hmm.
And the other thing about that, just to finish the
Yeah,
thought,
sure.
I mean, it would be an interesting conversation to have whether the Boost safe integer interface
Mm-hmm.
is the correct higher level interface.
Yeah.
The first problem I can see somebody bringing up
Yeah.
As the signaling mechanism, which I'm sure there are people in certain domains, probably your own
Yeah.
included, that won't like that.
Right.
But it would be an interesting conversation. This lower level facility is all good, but I think at the end of the day, application programmers are going to want something.
That's very true. That's very true. Like I deliberately excluded all of those concerns, how the high-level interface will need to look like. But this is a very interesting and a very important conversation that needs to be had. I just have the feeling that like this has the higher priority, right? Like if we want to get something into the standard, we should get this into the standard first, and then worry about the other stuff later, because this is the fundamental building block. And then there's enough to worry about later.
So, again, sorry, just to finish the thought on that, just to riff the opposite on what you just said, based on David Sankel's talk yesterday, there's an argument to be had that we should stop doing this, putting the low-level stuff in, which is relatively hard to use, and put high-level stuff in that just does it. But I understand the surface area of the higher-level interface is much more complicated to design and get through the committee than this kind of thing. And like
fair point. Like David Sankel argued yesterday that there's also a downside to standardizing the low-level parts first, because like they're not useful to the end users. They're not immediately useful, so they don't bring as much value. And yeah, I acknowledge that, but I don't agree with it. Like I think like at least in this case, the lower-level facility should go in first. But yeah, I'm happy to argue. Please.
I think that gives a lot of library writers the opportunity to make really nice high-level interfaces, and we can get a variety and then see what could go into it.
Yeah.
I guess the question though is, could you just put the intrinsics underneath, these libraries right now, without it going in the standard, right? If it's in the compilers, that's true. But on the other hand, I'll absolutely concede when you look at like the, bit algorithms that went into C++20, right? That is basically saying, look, here's a high-level interface to what is a compiler intrinsic in most cases, and here you go. It's a nice, clean wrapper around something that otherwise was painful to do.
Yeah.
Have you looked at safe numerics or any other libraries that use the type system to create proofs? So with safe numerics, for example, you can wrap an integer type or an integral type with like a range that you can prove that it will not exceed that range. And then when you do operations on it, the result of that operation, the type is updated with what the new bounds.
Oh, I see. Yeah. Now I see what you mean. So like the question was about safe numerics is the library. So it's like a library that basically encodes properties of the result of the computation into the type, so that you already get a lot of static checking through the type system and don't have to rely as much on runtime checks. And I think that's a very promising approach. I have not looked at that in too much detail, so I don't have any hands-on experience. But like this is definitely like, catching stuff at compile time is obviously the best.
That's something I'm very interested in.
Yeah.
And I've looked at that library and I'm also looking at some other options.
Yeah. Okay, cool. Then I think that's it. We're also about on time. So thank you very much for your attention.